So this is going to be a video just clarifying some of the things in the HW9 spec. So it's not a substitution for the spec, so you should still read that before you look at this video. We're just going to more or less like illuminate some of the topics and maybe go a little bit more in depth. So the three things we're going to go over are first NFA basics. So what I mean by that is like their relation to graphs as well as how they're represented in the actual assignment, like the nfa.java file. And then we'll talk about the matching algorithm. And then we're going to talk about the successors method, specifically in the case of epsilon. Okay, so first let's talk about the relation between an NFA and a graph. So after you read the spec, basically what you should have in your mind is that an NFA is a graph, specifically a graph with directed labeled edges. So what you see here, here's just an example NFA. So it has 4 states, so Q0, Q1, Q2, and QA. And then there's the different edges between them. They're directed, they have different labels. So what the labels mean here, for example, if we look at this edge label, this edge from Q0 to Q1, it's labeled A, and that has meaning in the matching algorithm, and it means that if you want to transition from Q0 to Q1, you need to consume a character A from the query string. So that part we'll talk about more in the matching algorithm, but just note that it has special meaning, in the matching / simulation process. Okay, there's 2 special states. The first one is the start state, and that's also, again, for the matching algorithm. In this case, it's just a Q0. On the diagram, we denote it with this, edge labeled start. Usually it'll have the name Q0, and there's only one of them in an NFA, so there's only one place there's only one start state. You'll see later, again, in the matching algorithm, you can possibly start at multiple startings, like states. You could start at multiple states, but there's still one start state. So we'll talk about that distinction over there. It involves the kind of special case of the epsilon edge. Okay, and the second type of special state is the accepting state. On the diagram is denoted with the double circle. So in this case, it's just QA that's accepting. And in our implementations, we're just going to have one start state. You might read online one accept state. You might read online somewhere that you can have multiple, and that's true, but in this implementation, the way we've built the NFA in the construction, like Thompson's construction, we have only just one start state. So you can read, there's something in the FAQ at the bottom of the spec if you're confused on that, but basically you should think there's one start state, one accept state, and a bunch of states in between them with all sorts of directed labeled edges. Okay, so that's what the NFA is. And in this part of the, spec walkthrough, I'm not really going to talk about epsilon edges, at least like in this part, because, even if this was epsilon, it's not really different than if it was B, right? It's just an edge labeled, with some label. The meanings of the labels, they're going to come up later when we actually do algorithms on this NFA. So here, nothing really special. Okay, now let's talk, so that's the representation. That's the structure. Now let's talk about the representation in the code. So first let's talk about the state class. The state class, the edges are represented as an instance variable, and it's a map from a character to a set of states. So the reason why it's a set of states is because you can, from one state, you can have multiple outgoing edges that all have the same label. In this case, let's take Q0 as an example, and let's write out what it might look like. So Q0, edges, so it's going to be a map. So it has A, right? That's one of the outgoing edge labels, and that maps to a set of all the states you can get to by taking an A edge. So that's Q1 and QA. So Q1 and then QA. Okay. So that's the first instance attribute. And the second one is accepting. So, and that's just denoting whether or not it's the accepting state. And in this example, the only one's QA. So accepting is going to be false for every state except for the accepting state, so QA. So here it's going to be false. Okay, and those are the different attributes of a state in the state class. That the start state that we talked about earlier, that's actually in the NFA class, not the state class. So a state itself doesn't know if it's the start state because it doesn't need to. We could have also done something like that for accepting because there's only one accepting state, but just to make it a little bit easier in the matches method, we just decided to add an instance variable that denotes whether or not it's an accepting state. So that might make the matches algorithm a little bit easier. Okay, so yeah, so the NFA class itself, it knows what is the start state and what is my accepting state. So again, if you're given a state itself, you can't tell if it's the start state or not. So we'll talk about that later in the matches algorithm. But okay, so that's basically it for the basics. So at this point, you should understand that an NFA is just a directed graph with labeled edges, and that the way we represent that in the code is through this thing called edges. You can think of edges as an adjacency list. In this case, it's more like an adjacency set, which is one of the representations of graphs. There's a few others. We just chose this one because it makes we'll see later, it makes the successors method a little bit easier. And then we also have this kind of accepting instance attribute, which just denotes whether or not that state is accepting. Okay, and then the start state and accept state are also attributes of the NFA class. So you'll see a lot of different instance attributes of the NFA, but these are the only 4 that you should be using. And it's okay if you don't use all of them because there's a little bit of redundancy between these two things because the NFA already knows its accept state. So maybe you'll only use 3 of these. But you definitely shouldn't be using any of the other instance attributes. For example, you shouldn't need to use the pattern instance attribute of the NFA class or any of the escape to pattern map or the concat or none of those things will be useful, except actually one thing I forgot is epsilon. So it's a character. And basically that's just to denote because we don't have an epsilon, there's no this in Java. So I have a special character that denotes that. So later on, we'll see you need to do certain things with epsilon. Instead of typing in this, you're going to want to use this static final variable we defined. But yeah, these are the only 5 instance attributes you should care about and use. Yeah, and you might not use all of them because, again, of the redundancy we talked about between these two. Okay, but yeah, that's the basics of the NFA. It's just a directed graph with labeled edges, and we'll see later on in the different algorithms what these edges mean, so what the labels mean. But just for right now, if you understand that this is a graph and that it's represented as an adjacency list, then you should be good so far. Okay, so that's basics. Now let's talk about the matching algorithm. So here it is. This is from the spec, directly from the spec. We did modify it a little bit from earlier today. So if it looks a little bit different, go ahead and just read through this, and we'll go over an example right here, and maybe the clarifications you hear might be a little bit more intuitive than like the block of text you see right here. Okay, so hopefully you had time to read that. So one thing I'm going to note is this set S is pretty important. So, and I'll show you why we need it. So let's say we have this NFA. Let me move it up a little bit. So let's say we have this NFA, and we'll have the query string, or I'll call it query, I guess. And let's have it be AB. Okay, So remember from the spec that an NFA can take a query string and it can tell you whether or not that string is in the underlying pattern it computes. So in this case, I've labeled it. The pattern is AB or AAB. And so we'd expect if I pass in either the query AB or the query AAB that the algorithm will return true. And on this graph, it's pretty easy to do like with your eyes, like pen and paper kind of style. So all it means for the query string to be accepted by the NFA is that there's a path from the start state. So the start state here is Q0. There's a path from the start state to the accepting state, QA in this case. And you can get there by only taking edges in this order, right? So first I'll need to take from Q0, I need to take an edge, A. So we'll call that consuming A. So once you consume it, you can't take it anymore. And this is where the non-determinism comes up. Because from Q0, we have two options. I can either go to Q1 by consuming A, or I can go to Q3 by consuming A, right? Because these two are labeled A. So, and that's why over here, right, it's the edges is a map from character to the set of states, right? Because you're allowed to have multiple outgoing edges all with the same label. Okay, so that's the non-determinism. So you may be wondering, like, which one do we choose? Let's say, you're doing this, again, this is like you pen and paper style. Let's just say you choose the bottom one, okay? So you've consumed A. I'll just cross it off to denote that we consumed it. Okay, so we consumed A, and we transition from the start state to Q3. So now we're in Q3, okay? And now we need to consume the character B. Well, Q3 doesn't have any outgoing edges labeled B, so we're stuck. That does not mean like we stop here. It just means we automatically kind of return false. Like there's no place this NFA would, like if we took this bottom A, the NFA wouldn't like stop here. The algorithm would halt and it would kind of end early because there's nowhere to go. So basically, even if this was an accepting state, this string is not accepted. It doesn't stop here. It just, the algorithm terminates and it returns false because you need to consume all the characters for you to be considered accepting. Okay, but it's not an accepting state, so I'm going to undo that. So it turns out that our first guess of going down was bad. Okay, what if we instead went and took this top edge? Okay, so this is kind of in a parallel universe if we decided to go up instead of down. Okay, so we consume A, and now we're at Q1. And now we see a B, so we'll consume B, and there's only one B, so there's no non-determinism. We consume B, and now we're at Q2. And I'll underline the states we can possibly be in. So we could be in Q2, or we see this epsilon edge here, and that means we could also be in QA, because epsilon is, you can think of it as like a free ticket. It doesn't consume any characters, because epsilon represents the empty string. So we're always allowed to take an epsilon edge, and it won't consume any characters. So even though we've consumed A and B, we've ran out of things to consume, we can always take an epsilon because they're free. So we could be in Q2. We could decide to stop in Q2, or we could decide to pick up the epsilon for free, take the epsilon edge for free and end in QA. So again, there's a little bit of non-determinism. Let's say we decided to just stop in Q2. Well, there's no more characters to consume, and Q2 is not accepting, so that was a bad decision. So far the two there's 2 out of the 3 possibilities for where this query string could end up have caused it to be rejected. But there's still one more place it could possibly be, and that's if we took the epsilon edge and went to QA. So let's take it. Let's go here, and we could decide to end here. And it ends in QA. There's no characters left to consume. We've iterated through all of the characters in the query string. So, and we're at QA. QA is an accepting state. So we say that the string is accepted. So AB is accepted by the NFA. And that's good because we kind of hoped it would be, because it's part of the pattern. So I'll put a star at the places. So we could have stopped here. We could have halted here or there. I'm not going to put a star at Q3 because that's not a valid place to stop, because we had unconsumed characters there. Some implementation or some places will have kind of force you to have every state have a valid edge. So what you'll see, and you'll see it in this example, you kind of have this like QF, which means like it's like failure state, or maybe people call it QR, like the rejecting state. And if you ever mess up, basically you'll end up there, and then you'll just you'll loop there forever. Like if you're in that state, it means there's no possible way for you to be accepting. So you can kind of read through this NFA if you want a little bit more of an idea on that. But it's also totally fine for us to not have an outgoing edge labeled B here. Like it's okay for us to not have that edge, and it just means that the NFA gets like stuck. It can't go anywhere. Okay. So now let's go over the algorithm. So to account for this kind of non-determinism where we could have gone to Q1, right? At the very beginning, let me undo all this. At the very beginning, we could have gone to Q1, or we could have gone to Q3. We're going to maintain a set that kind of keeps track of all the places we could be in at the current moment. So let's backtrack a little bit, and let's see how that set starts off. Okay, I'm going to call that set S. And this is now we're going to follow the algorithm here. So this is the formal way of doing it. And one thing I'm going to note real quick is I'm going to kind of split this up into two parts. So actually, we'll talk about that when we get there. So first, let's take step one. We initialize our set to be our set. We'll call it S, and it's just going to be Q0 as well as any of the states that Q0 can reach by only taking epsilon edges. And this includes successive epsilon edges. So if a state is one epsilon edge away, or two successive epsilon edges away, or three successive, etc., they should be added to S. And let's think about why that makes sense. So here, maybe this is a bad example. There's no epsilon edges from Q0. I'm just going to draw one. Let's pretend we had this. Q6, Q7, and that's epsilon 2, all the way to, I don't know, let's just do Q100. It's a nice even number. And let's just say that they all have epsilon edges going towards them. And now I've kind of like departed from the fact that this is like an NFA for the pattern, blah, blah, blah. I'm just adding this epsilon stuff as an example for why we need to do that. Okay, so the reason is because we said S kind of defines all the places we could be in at the current step. So to initialize S, we always start at the start state, right? But I also said you can consume epsilon edges for free and not consume any characters. So for this query AB, I could start in Q0, or I could decide to, from Q0, take an epsilon edge to Q6 and start there instead. So maybe I want to start here. And that would be totally fine because I haven't consumed any characters of the query string, right? Because AB, this is an epsilon edge, it's not A or B. So we take it for free. Or I could decide I want to start in Q7 by taking two epsilon edges. So unlike, for example, when Q0 wants to take an A edge to iterate on the first query string, we can't take 2A, like we can't go from Q0 to Q3 and then Q3 to Q4 because that's consuming two A's because you can only consume one at a time. But epsilon, it's not restricted by this. It's for free. So you can take two, you can take three, you can take however many you want. You can start at anything from Q0 to Q6, Q7. You can even start at Q100 by taking, 96, 95 epsilon edges. So that's basically why that's why the epsilon case is different. And that's not going to be handled in this matching method. It's going to be handled in the successors method. So let me underline that. The this part, I guess the bold part here, that's going to be handled in the successors method. And we'll talk at the bottom of this, or sorry, at the end of this, why, like a little bit more why, and then a little bit about how you can actually do that. But that's a little bit of the intuition on why it should be like that. Okay. So if this, we're at step 1, so we're initializing S. So it's going to have Q0, as well as any states Q0 can reach by only taking epsilon edges, and that could be consecutive. So I guess this probably would have Q6, Q7, all the way to Q100. But let's just, in this case, let's just delete that stuff. It's not going to be useful for the rest of it. Okay. Yeah, so I'm just going to remove that stuff. I think the point got explained. Okay, so we initialize our set. Step 1 is done. Cool. Now let's move on to this next thing. So this next thing is a for each blah, blah, blah. So this is the part where this is basically what we did in our example. So first we iterated on A, then we iterated on B, and then if there was another character, we would iterate on that character, and so on until you run out of characters in the query string. So to put it formally, for each character in the query string, so first C is going to be, like first is variable C is going to be A, because A is here. And then it's going to be, after that whole iteration, then it's going to be B, because that's the next one, and so on. Okay. Now we can, okay, so let's iterate on it. So C equals A. Let's write that here. So C equals A, because that's the first character. We're still using the same query string, by the way. I don't know if I said that. So C is A. Now create a new empty set S new. Okay, so this is the part that we clarified in the spec. It wasn't there before, and we did not use it in our example. And that's because this is this is basically a hint for the programming aspect of this. Because, if, for example, if this was just S, then what you're going to get is you're going to get a concurrent modification exception. And what that means is, it means you're iterating over the set S, but while you're iterating on it, you're adding to S. So, and that, even if S was a list or a stack or something like that, the same thing would happen. So you can't iterate on something while you're modifying it. So you can't be removing from it, you can't be adding to it, you can't do any of that. So that's why we define S new to help us with that, because what we can do instead is while we iterate over S, we can add our things to S new and then do this, set S equal to S new. So then you won't, earlier in the spec we had this example with removals. Now you won't even need to remove anything. So now basically you can just use add operations, and you'll be totally fine. I think the remove operation kind of confused some people, so we just decided to take that out. Okay, so S new, again, just to clarify, it's only for the programming part. So in the examples, I'm not going to talk about, I guess maybe in these examples, I'll talk about S new, but in this examples in the spec, they're not there. So if you're looking for S new in the spec, it's only for programming. Okay, so let's see. Let's read our directions. Now we're going to iterate for each Q and S, and this kind of was different than what we did in our examples, because in our examples we kind of tried each path separately. And remember, in this case, we're trying all the paths at once. So first S is Q0. We're going to see after this S is going to contain Q3 and Q1, because we can get to both of those states by taking the first character, which in the query string, which is A. In our example, we kind of did like a depth first. First, we tried this path, then we tried this path, then we tried that path. But in this case, we're going to try all of them at the same time. And that's by using the set. Okay, so in this case, we just started, so S has one thing in it. So Q, in this case, I guess we'll say Q equals Q0, because that's the only thing in S, right? So for iterating over S, it's just that. Update our set S. Okay, I forgot to make S new. S new is empty. And I'm going to put some space there because I know we're going to add stuff. Okay, update our set S new by adding all states Q new. That Q, remember Q is Q0, that Q has an outgoing edge to with edge label C. Remember C is A. If no edges are labeled C, then don't add anything for this state. Okay, one aside I want to make is this kind of logic, by adding all states that Q has an outgoing edge to with edge label C. This should be basically a one-liner, maybe two-liner, using your successors method. I don't know how to spell it, so I'll just get as close as I can. And it takes in. Well, yeah, maybe okay. I'll leave it as that. You're gonna use your successors method. You can figure out what the parameter should be. I think it's pretty self-explanatory what your parameter should be. But that'll also handle this kind of blurb here at the end. If no edges are labeled C, then don't add anything for this state. It should handle that if you have all three cases that we talk about in successors. But we'll get there later. Okay, let's do that. So S new. So we're adding everything to S new that Q0 can reach by taking an A edge. Q0 can get to Q1 or Q3. So that's what S new will, we'll add Q1 and we'll add to Q3. Okay, and that's it for that iteration. So what's the next Q in our set S? Well, S only had one thing, so we're done with that for loop. Okay, so this part is done. And now we're going to do this step, the set S to S new, and make S empty again. Okay, so I'm going to do this. I'm going to say S is that. Okay. I'm going to make S that. And now make S new empty again. Okay, we can do that easy. S new, it's this empty set. And I'm leaving it, no space because I know that we're not going to add anything. Okay, we're not done yet with this iteration. So C is still A, right? We're still in this loop here on the first iteration. We're not done. We're not quite done yet. And now this is where I'm going to talk about the different halves of this part. So this first part that I've labeled this curly brace, that's accounting for taking the C edge. The C edge. C being the variable name, right, of the character. And this next part is taking into account that we can always take an epsilon edge for free. And it doesn't consume any character in the query string. Nice. So now this part is going to be taking, or let's make it plural, epsilon edges. Because remember, we can take 2 successive epsilon edges or 3 successive epsilon edges, whatever. And just like how so it's basically this kind of first part of this, the algorithm, where it's like any states reachable from Q0 via only epsilon edges. So just like that was part of the successors method, same thing here. So successors, something like that. So basically you're going to iterate over all the new states in this case. And remember, we already set S to S new, so S contains the new state, right? So we're iterating over S. And now we're going to see, okay, what states can I like to think of it as like expanding from S by only taking epsilon edges, because S is it's an incomplete set. Like it doesn't have, because we said at the beginning, S will contain all the states that we can possibly be in at that step of the algorithm. But if we don't include this second part, the taking epsilon edges, we're not accounting for the fact that you can take epsilon edges for free. So if you don't have this part, you're not going to be passing stuff like a lot of the A plus / like A star, basically anything that has like a star or a plus in it in the pattern, you won't be passing those tests, which is a lot of them. Like it basically all the simple, medium, and hard. Okay, so it's important that you add the second part, the taking epsilon edges. And it's probably going to look pretty similar to the first part, taking the C edge, except instead of C, you're going to be using epsilon. Okay, in this case, none of the states in S, Q1 or Q3, have an epsilon edge, so nothing happens. S new stays empty, and then when we do this part, we're adding nothing to S, so S stays the same. Okay, and now we claimed that S is now ready for the next iteration. Let's see if that's true. So our set S is Q1 and Q3, and we've consumed A. So A's been consumed, so we only have B left. And so far, it's an accurate representation of all the possible states we could be in. After consuming A, you could be in Q1, or you could be in Q3. You can be in either one, and that's it. You can't be in anything else. Remember that you can't be in Q4, even though there's an A edge here, because that would be consuming 2 A's in a row. Since we've only seen 1 A, you only get to consume 1 A. Okay. Whoops. Weird. Okay. Okay, so that's the first iteration on C. Now we're on this second iteration. So the second iteration of this loop. So let me delete that part. So now C is B. And now we actually have multiple things in S. So we're going to have a little bit more, what's it called? I guess action in this iteration. So first let's first Q, let's just make it Q1. Okay. So now we're at this part, right? The for each Q and S, blah, blah, blah. So update S new by adding blah, blah, blah. So basically we're just going to go to Q, which is Q1, and we're going to take our B edge, because, right, C equals B. So S new, we're going to add Q2. Q2. Oops, I'm not going to close it quite yet. And okay, that's it, because, if I can only take one B edge from Q1, that's the only place I can end up, is Q2. Okay, now let's look at the next state in S, which is Q3. Right, Q3. And from Q3, what states can I go to by taking a B edge? None, right? There's no outgoing B edge from Q3. So just like the spec says, if no edges are labeled C, then don't add anything for the state. We're not going to add anything. So S new stays the same. And that's it. That's the last state in S. So S new just looks like this. Okay. Now we set S equals to S new. Okay. Let's do that. S equals S new. So I can just, I'll do this. And then it also says clear S new. So make it empty. S new equals empty. And I put space there because we'll see why. Now for every state in S, and in this case, there's only one state in S. It's not a big deal. Let me also erase these two things. So for every state in S, we need to add all the states that we can reach by taking any number of successive epsilon edges. So remember this part. This is your successors method that you wait. Did things get moved around? Weird. I don't know how that ended up there. Okay. Well, anyways. So yeah, that part of the spec should be implemented in the successors method, not this method. So it won't complicate this method at all. It just means your successors method will have a few different cases depending on if the character is epsilon or if it's not epsilon. But okay. So now we're at Q2, and we need to update S new to be all the places Q2 can get to by taking an epsilon edge. And it actually can take this epsilon edge to QA. So S new is QA. And that's it, right? Because this epsilon edge is going the other way. So it's from Q5 to QA. So we can't take it. The direction's wrong. Okay, and now we're going to add all the things from S new to S. So that's QA. And that's the end of that iteration. So let me underline all the places. in S. So it's Q2 and QA. And again, like we claimed earlier, S is now ready for the next iteration. Like I said here, that is true. Oops. I think maybe I moved it last time too. But yeah, that's still true because S is Q2 and QA. And after I've consumed A and B, those are the only two places I can be, right? Because that means I could take this path, consuming this A and that B. Or I could take this path, consuming the A, the B, and then taking the epsilon for free. So it does work, right? It's doing exactly what we said it would be doing. But it's important that you're taking into consideration this part, right? The taking the epsilon edges. If you don't, then it's not going to work. So make sure that you're going to have two kind of parts in your code that will look pretty similar, right? The taking the C edge, that part of the iteration, and taking epsilon edges, those two parts should look pretty similar. So if you follow this spec here, you should get a working. We should all basically have the same version of matches. They will all look basically the same. Okay, so I'm gonna assume that we that's probably enough explanation for that part. Now let's talk about what's next? The successors method. Okay, so just like the Java doc for the successors method says, there's three different cases, and I kind of wrote it in English here. So it's up to you. I think you can on your own write it in Java. So, okay, remember the successors takes in a character C, and basically we want to know what states can I be in after consuming this character C. So there's the three cases are if this state does not have an outgoing edge labeled C. Actually, I'm going to change it from to just that because it's a variable, right? Maybe it's not actually the letter C. But if it doesn't have any outgoing edges labeled that, you need to return an empty set. So I just wrote hash set because tree set won't work because they're not comparable objects. So I think most people use hash set anyways, so it shouldn't be a big deal. But that should definitely be one of your cases. If you don't have an outgoing edge labeled that, then you need to return empty set. Okay. Now the next two cases, I guess we're giving that one away. It's in the spec, I think, or it's in the Java doc. I think most people would get that anyways. The next two, no, we're not giving away, but we'll give hints and maybe a little bit more explanation. If the character C is there, you do have an outgoing edge labeled C, and that character is not epsilon, so that's what I wrote here. It's not epsilon. Then it should be a one-liner. It should be using the different instance variables that we talked about earlier from the state class to return a set of all the places you can get to by just consuming C. So if you find yourself looking at the different instance attributes of state, then you're on the right track. And I think one of them is more informative than the other. So I'll leave that to you. Okay, and the last case, the confusing one for most people, is if you do have that, if C isn't outgoing, you do have an outgoing edge labeled C, and C is equal to epsilon. So in that case, what I wrote here in English is return a set of all states you can reach by taking only epsilon edges, including successive epsilon edges. So remember that that there's no way to consume epsilon because you get it for free, right? Because it's the empty string. So I thought I had an example, but maybe I didn't. So let me just draw a random. Let me talk about related problem from lecture 33. So okay, lecture 33. Let's say I have this graph. So that node is labeled 0. That node's 1, 2, 3, 4, 5. And let's link them up like this. 1, 2. Let's do it that way. Okay. So, and let's say I want to know, starting from this 0 node, I can draw that better. Starting from this 0 node, what are all the different nodes that I can reach? And in this case, it's pretty easy, right? You can just kind of follow through, and you'll see that it's 0. Or I guess let's just not include 0 to be let's just say all the ones besides 0 that you can reach. So I can reach 1, I can reach 2, and I can reach 3. And you learned an algorithm from lecture that will allow you to do this. It's a graph traversal algorithm, and it's called DFS. Now, a related algorithm, I don't believe was in that lecture, is BFS. It's very, very similar to DFS. The only difference is instead of using a stack, we use a queue. But we're not really going to talk too much about that. So if you're confused, you can, I'm sure you can find like something on Wikipedia. It's probably the first thing that comes up, like some pseudocode, and you can look at that. But yeah, these are the two algorithms, DFS and BFS, that will be your friend in this problem, finding all the reachable nodes from 0. And I hope that you can see that this is a related problem to the NFA, because what if I did this? What if I labeled these epsilon, 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 I don't know, A, let's put that epsilon 2. Now it's basically the same problem. The only difference is that you don't actually consider every edge. You also want to make sure that edge has the correct label, namely the label epsilon. If it doesn't have the label epsilon, we're just going to basically pretend like it's not there. So maybe you can think of, like, you're not actually going to delete edges, but for the purpose of this problem, you can basically pretend that this A edge isn't even there. It ends up not affecting this answer, but, you know, maybe if that was an A, you can pretend it's not there, right? And then it does affect the answer. Okay, but let's bring this back. Okay, so the one that you learned from lecture was DFS, and there's two ways to implement this. So you can do it recursively, or you can do it, well, I guess that was kind of obvious. You can either do it recursively or iteratively. And both ways, recursively and iteratively, use a stack. So recursively implicitly uses a stack via the recursion stack, like just based on the recursive call of programs. And iteratively, you actually use like an actual stack. So you'd be importing java.util.stack, and you'd be using that. In this problem, for the epsilon case, you can do either of these. I think I would recommend doing this one, because if you did it recursively, it's a little bit tricky because in most like your method would look something like this. I'm just gonna call it DFS, and it would take two parameters. It would take, you know, where am I starting from? So state S, as well as where have I visited? So set of states visited. So visited or marked or whatever you want to call it. And our method is successors car C. So this part is kind of already taken into account because it's an instance variable. So if you're in successors and you want to get the current state, you just say this. So that's good. We don't really need to worry about that. But the second part, we can't. There's no way to pass down this set of visited states in this method's successors. So if you wanted to do it recursively, you would have to define a helper method that did take in this set of visited states, and then you could do exactly what you saw in lecture. Also, it's pretty similar to like in Project 2 Loa, the like num contig method, basically pretty similar to that. But I don't know. I think when you start including helper methods, it gets a little bit confusing. The iterative version, you can do all inside the successors method. No need for recursion, just using the stack. So that'd be using like the java.util.stack. You can also use BFS, and I don't think you can do BFS recursively, so there's only an iterative version. And there you'd be using the java.util.stack I think that's how you spell it, Q. And I believe it's an abstract class or maybe an interface, one of those things. And so you'd probably instantiate it with like a linked list or an array list or whatever you want. So yeah, those are some, I guess, coding tips for the epsilon case. And remember, that's only in this case. Everything else, like if you need to return an empty hash set, or if it's not equal to epsilon, you do not need to do anything like this at all. It should be no graph traversal. Both of them are one-liners. We kind of gave this one away, but the other one, it's not too hard. I think if you look at the instance attributes, then that'll be a big giveaway. Okay, yeah, so that basically concludes the, I guess, spec walkthrough here. If you have any conceptual questions still after this video, there's a Piazza thread on it, homework 9. It has some questions already, so just do a quick check so you don't ask a duplicate. And if you have coding questions, there's a lot of questions already on the coding questions thread, so just double check again that it's not a duplicate. There's a lot of good questions on there, good discussion. And if you're just like stuck on like a bug that you know what you're doing, you just can't seem to find just like one small bug, feel free to submit a Git bug and we'll get back to you. But yeah, so that's it. I think maybe I can put this these notes in like the description or something. So yeah, that's it. Bye.